Thank you, Frank. Good morning, good afternoon, good evening to all of you from wherever around the world that you're joining us today. For those of you who don't know me, my name is Shahram Amini. I'm the Director of R&D at Pulse and co-chair of the Biomedical Coatings TAC at the SVC. On behalf of all my colleagues at the SVC, I'd like to thank you all for attending today's keynote lecture. It is my absolute and distinct pleasure and great honor to welcome Professor Stuart Cogan as our today's keynote speaker. Professor Cogan is a professor of bioengineering at the University of Texas at Dallas, where he conducts research on neural stimulation and recording with emphasis on thin film electrodes, materials, and devices. His current research primarily focuses on the development of microelectrode arrays based on amorphous silicon carbide and the application of ultra microelectrodes as neural interfaces for the brain and the body's peripheral nervous system. Prior to joining UT Dallas, Professor Cogan was Vice President and Director of Advanced Materials Research at EIC Laboratories. He received his Bachelor of Science degree in Mechanical Engineering and a Master of Science degree in Material Science from Duke University in 1975 and 1977, the year I was born, respectively. He obtained his Doctor of Science degree from MIT in 1979. He was a visiting professor in mechanical engineering and material science at Duke University, where he worked on amorphous semiconductor materials for solar cell applications. And then he returned to MIT as a research associate in 1981, focusing his research on microfilamentary metal matrix composites for compound semiconductors. He then joined EIC Laboratories, and his research interests there included thin film electrochromics for optical switching devices and coatings, materials for encapsulating implanted medical devices, and thin film electrode materials for stimulation and recording in neurostimulation and cardiac pacing applications. So that was the easy part, reading his bio, reading off of his bio, my personal take from Professor Cogan. So I started working on biomedical coatings and the field of coatings and thin films for neurostimulation applications almost 7 years ago. I had no clue about this field, but today, every paper that I read in this field, I find a link, a connection to Professor Cogan. I have read so many papers and I realized, wow, these are wonderful papers and articles that have been published. As soon as I look at the authors and the list of co-authors, Professor Cogan is one of them. So I am extremely honored to know you, and I'm really grateful that you've accepted our invitation for today as a keynote lecture. Thank you so much. Without further ado, Professor Cogan.
Well, thank you very much, Shahram. So let me get started right away. So I'm going to discuss some of the work that we've been doing on actually sputter deposition of electroactive coatings for thin film neural interfaces. And a lot of what we do is probably anathema for the general society of vacuum coating practitioner, because we're very interested in hydrated coatings, and coatings with porosity. And I think before we get into some of the details of deposition processing and coating structure, I need to give you a little bit of background on what thin film neural interfaces are and how those interfaces actually work, so that you can see what motivates us to create such structures that we're interested in. So specifically, we're interested in electrical neural interfaces, and electrical neural interfaces are interfaces that allow for stimulation of neural activity by imposing electrical currents, usually pulses of electrical currents as a function of time, or recording neural activity. So we put an electrode into the brain or into nerve, and we just measure the electrical activity associated with neural activity. And there are a burgeoning range of applications for electrical interfaces or neural interfaces to the body. And I've listed a few here just for background. Parkinson's disease, sensory prostheses, that means vision prostheses, auditory prostheses, volitional control. This means devices that go into the brain that record brain activity that can be used to control an extracorporeal device. But there are a broad range of other applications that are that are coming over the next few years, a number of clinical applications that are coming. And so to highlight something about neural coatings is that, generally speaking, electrodes, which are where the neural coatings, these electrode coatings are placed, are very small. And I've just shown some examples across the bottom of the screen here. This is an electrode site here. It's about 400 microns in diameter. Here's an electrode site on the tip of a penetrating electrode. It has an area of about 2,000 square microns and so on. So we're really talking about very small electrodes. And the focus of the talk today is going to be on planar electrodes, like these electrodes or these electrodes, but non-planar electrodes with a great deal of surface geometry are also of interest. So my focus is going to be on electrical stimulation. And so when we deliver therapeutic electrical stimulation, a couple of things we should appreciate. The first is, and those of you who are in this business might recognize this structure here as the distal end of the Medtronic deep brain stimulation lead, but that's really not the point. We have, I'm showing two electrodes on this lead, an electrode here, an electrode here, and a couple of wires coming down from some source of these electrical pulses. And obviously in the wires and in the electrode materials themselves, current is carried by electrons. But out here, in the tissue out here, current is carried by ions, either cations, the C+, or the anions, the A-. And something has to happen at that interface between the electrode and the tissue to change current flow from electron flow to ion flow. And the important take home from this part of the slide anyway is that that transition from electron to ion flow involves both electron conduction and ion conduction. So wherever we go here, we have to keep in mind that we have to worry about the transport of ions and the transport of electrons in order to get the current flow from the electrode into the tissue. And current flow, as you may think, can be reductive current flow or oxidative current flow, and oxidation by any other word is corrosion. So we have to be very careful to avoid damage at electrodes when we do neural stimulation and avoid damage to tissue. And so we do that by delivering so-called biphasic pulses. Here's a negative pulse and here's a positive current pulse. And the net charge, the current times the time for these two pulses is zero. So in principle, we start off where the electrode starts off, the electrode ends up after we've delivered the pulse. So there's no change to the surface of the electrode. That doesn't really happen, right? But that's the idea of delivering biphasic stimulation pulses. And to give you a sense of the stimulation parameters, I've shown just a series of biphasic current pulses. Typically, the currents, which I think, and the charge, which are the things that are most important for us to consider, range from as low as a microamp, actually in some applications up to 20 milliamps. But the range that we're going to be interested in for the devices or the coatings that I'm talking about today are in about the 1 to 100 microamps. And that 1 to 100 microamps, that would be the magnitude of one of these, the phases of one of this current pulse. And typically these phases, each is about 200 microseconds long, only 200 microseconds. So it's a short burst of high current. And the charge per phase, this is one phase, this is another phase. The charge per phase is modest, on the order of, well, 0.2 nanocoulombs, maybe up to 5 and, well, it says 5 microcoulombs there. That's the large devices. For the devices I'm talking about 0.2 nanocoulombs up to about 20 nanocoulombs. But while these currents may seem modest and the charge per phase modest, it does result in very high current densities. at these electrodes because they're so small. So we may have current pulses. They're only 200 microseconds long, but they deliver up to 2 amps per centimeter squared, or the current is passed across that interface at a fairly significant current density. And so how do we deliver the charge across the interface? Well, there are 2 ways to do that. One is by capacitive charging and discharging of the electrode double layer. What that means is we have electrons in the metal, we have ions in the tissue, and that they accumulate or charge or discharge at the interface between the metal and the tissue without any chemical reactions going on. And that's called capacitive. And that's actually, capacitive charging is really preferred in many respects because there are no side reactions going on. Nothing is being oxidized, nothing is being reduced, there are no pH changes next to the electrode, and so on. It turns out, as you'll see in a few slides, while capacitive is very desirable, it's often doesn't achieve the necessary properties we need for neural stimulation. So that leaves us with Faradaic. So Faradaic charge injection, that involves oxidation and reduction of species at the surface of the electrode, and as you'll see in a minute, also oxidation and reduction within the bulk of a 3-dimensional film that is coated on the surface of the electrode, and it's those films we're interested in depositing by sputtering. So Faradaic is necessary. I won't say it's a necessary evil, but it is something that is necessary, and we have to be much more careful about how we use Faradaic electrodes if we don't want to damage the electrode or the tissue. So let's look a little bit at these charge injection mechanisms that I was just describing. And I show in this slide three examples, and this is of charge injection. At the top, titanium nitride. This is the prototypical double layer charging or capacitive electrode that's actually used extensively in the cardiac pacing industry. And I've shown it on the, if you look on the left-hand side, this region is the metal electrode or the metal substrate. The black is the titanium nitride coating that it's deposited on. And what happens is at the interface here between the tissue out here and the titanium nitride coating here, at this interface, we get electron and ions accumulating to accumulate charge that can be discharged or charged at this interface to deliver capacitive current from the electrode to the tissue. So you'll notice again that I'm emphasizing electrons in the titanium nitride, ions in the tissue. Now, the more interesting Faradaic, with all due respect to titanium nitride electrode aficionados, the more interesting material, Faradaic material, is prototypically described by iridium oxide. So iridium oxide has been around for about 30 years, something like that. And it is increasingly used in neurostimulation applications. It delivers charge to the tissue by virtue of a reversible iridium 3+ to iridium 4+ oxidation reaction that occurs within the bulk of the film. So if we look on the left-hand side, here is the metal substrate. The white now is the iridium oxide film that has been deposited on the substrate. And you'll notice that in the iridium oxide film itself, I've shown both electron conduction and ion conduction. And so a key feature of these redox coatings or these electroactive coatings, let's call this an electroactive coating. A key feature of these electroactive coatings is the coating material itself must exhibit both electronic conductivity, so it conducts electrons, and it must conduct ions. So we have this somewhat conflicting requirement to have electronic conductivity and ionic conductivity within the bulk or within the structure of our coating that is on the surface of the electrode. So let's talk now about how we're going to make these coatings, right? So we're going to think about iridium oxide coatings and extend the iridium oxide to ruthenium oxide, which is another electroactive material, and ruthenium titanium oxide. And we're going to deposit these coatings by sputtering. So let's look and see how we're doing that. Okay, sputtering electroactive oxides. Right? So we do it in a sputtering system, obviously, but there are a couple of things about what we do that are a little different from typical. The first is that this is reactive sputtering, so we have iridium metal targets or ruthenium metal targets, but one of the species we use to oxidize the metal is water vapor. So we have gas flow of argon typically, some oxygen, and some water vapor. And we find, as we'll go through the presentation, that water vapor is particularly effective in producing films with good properties. And so after some trouble and some expense, we were able to build a vacuum system that would allow us to control through a mass flow controller the water vapor ingress into the vacuum chamber. And then the other thing just to keep in mind here is that this is the sputter down mode. The substrate holder where we have our electrodes to be coated is rotating. And it's rotating at about 60 RPM in and out of the plasma. And so that the actual substrate itself is under the plasma probably less than 10% of the time during the sputtering chamber. And so that really results in minimal substrate heating. So why water vapor, all right? And so some years ago, actually more than some years ago now, 25 years ago, when I was at EIC Laboratories, we determined that sputtering, in this case it was iridium, in hydrogen gas and oxygen gas mixtures produced films that had very good electrochemical properties, produced iridium oxide films with very good electrochemical properties for neural stimulation electrodes. And this was published over the years. But one of the things that was the hallmark, I suppose, of this sputtering process, that when we were doing optical emission spectroscopy to monitor the plasma, we would find that the presence of OH in the plasma was a good indicator of achieving films with good electrochemical properties. So this then led to, well, there were some reasons why we didn't want to use hydrogen and oxygen gases. And so this led to the use of water vapor. And so the previous slide was 25 years ago. This slide is last year and the year before. And so we're now introducing water vapor into the sputtering chamber, and we're examining the plasma by optical emission spectroscopy and seeing again the formation of this OH signature in the optical emission spectra. And this then leads us to actually two questions. One is, can we control the deposition process in which we're using water as an water as a reactive species? And the other is, how good are the electrochemical properties? So let's see about, first of all, control. And so the experiment's fairly simple. We have a certain flow rate of argon into the chamber, certain flow rate of oxygen, which we change, 30, 25, 10, 15, so on, SCCM, and of water, such that it's 15 SCCM of argon, and then the combined flow rate of oxygen and water is 30 SCCM. So we go from only oxygen at the top to only water as the reactive species on the bottom. And we use emission spectroscopy to monitor whether or not we have good control over the content of the plasma. And this is shown in some of these diagrams, specifically B, C, D, A, B, C, D, E, F, G here on slide A. This just is showing you the different gas flow rate ratios for the oxygen and the water vapor. So you can see, for example, that by increasing the water vapor content, that's going in this direction, right? We are increasing also the OH content, right? So there's a clear relationship between the water that's going into the chamber and the concentration of both the hydroxyl and hydrogen species and so on in the plasma. So I don't want to go into any details about this, but we can look at the hysteresis in these data and so on. But the bottom line is we have pretty good control over the amount of water. So the question then is, we have these 7 deposition conditions. I think actually, if I count properly, 1, 2, 3, 4, 5, 6, 7 deposition conditions, at least highlighted here. How does that translate to the morphology of the films that we're depositing? So here's the first bit of really vacuum science, right? And this is now, or at least thin film science. So this is the morphology of a sputtered iridium oxide film. These films are about 300 nanometers thick, right? And we have a scale bar here for reference, 200 nanometers, and this goes from oxygen all the way through to water, so pure oxygen to pure water. And you can see an evolving morphology of this film, and these morphologies are quite reproducible for the different deposition conditions that we were investigating. And similarly, for ruthenium oxide, which we deposit in exactly the same way, we get a change in the morphology of the film, going from a purely oxygen to purely water vapor as the reactive species. And if you look at the cross-section of these films, this is a cross-section of the ruthenium oxide film with an oxygen to water ratio of 1:3, you can see that it very much follows a typical structure zone model with more or less a zone 1, and which we're very interested in because porosity is everything for us. So this is the importance of porosity in morphology. This is an example of a sputtered titanium nitride film now. So titanium nitride is a capacitive electrode material, and it relies on having a very high electrochemical surface area or available surface area ratio to the geometric area of the film. And that surface increases that electrochemical surface area, in principle, increases the amount of charge available. And so Q is charge, C is the double layer capacitance in farads per unit area, A is the area, V is the voltage. The larger the A, the larger the Q, hence the desire to make these films as porous or have as much available surface area as possible. That comes with a problem, however, it's because porosity is limiting. And this is a cross-section of a titanium nitride film. These are titanium nitride grains. So, and these are, as is shown here, these are electron conductors. But in between these grains are electrolytes where the anions and cations can diffuse in. However, there's a problem here. Problem is, this is a long way down this pore structure, and that creates a pore resistance, which is limiting. And this just shows what that is. This is a titanium nitride film. Here is a pore. In that pore, the R's are the resistance of the electrolyte, and the capacitances are the double layer capacitance as we go down the length of this pore. And the bottom line is that these resistances and capacitance create a time constant. That time constant is a lot longer than the 200 microseconds we need for a current pulse, so we don't access very much of this pore. And so this brings us to the question of what can we do to select a film that has a surface morphology appropriate to stimulation. And so this is what we're doing for iridium oxide. What we're doing, or ruthenium oxide, we're creating films that maybe in an ideal way have a certain modest amount of morphology, but importantly, as shown here, these films have both ion and electron conductivity within the bulk of the film. So this is the key here, is that we're making materials that have both ionic and electronic conductivity within the bulk of the coating. So quickly then, the quick just view of electrochemical properties. We do two things. We do cyclic voltammetry, really need to know what that is. Well, we do voltage transient measurements. And they create, from those measurements, we get two things. Cyclic voltammetry, we get something called charge storage capacity. That's the total amount of charge that could be available to deliver a stimulation pulse. And we get charge injection capacity. Charge injection capacity is how much we actually get in a stimulation pulse. And the charge injection capacities and the charge storage capacities, not surprisingly actually, depend on the morphology of the films. And so this is an example of cyclic voltammetry of, this would be iridium oxide, and showing the different morphologies on the CV diagrams. This is just electrochemical potential, this is current, so this is actually, think of driving force, think of the rate of reaction, think of the area within the CV, this area in the CV being the important phenomenon, the important feature. So the more area, the better the film likely is. And so for, it's basically cutting a long story short, and a lot of electrochemical measurements after that, what we found was that the oxygen to water flow rate ratio, a gas ratio in the plasma of 1:3, produced films with the highest charge storage capacity, and high charge storage capacity is desirable. Likewise, those films, and this is charge injection capacity, this is how much charge actually can be delivered. The 1:3 films, oxygen to water ratio, also has the high charge injection capacity, and actually they also have somewhat lower impedance. Low impedance is desirable, high charge capacity, high charge injection capacity are desirable. So these films suggest that an oxygen to water ratio of 1:3 is desirable, right? And it turns out to be exactly the same with ruthenium oxide. So here are the SEM images of the surface of ruthenium oxide. Water only, oxygen only is the oxidizing species. Water only is the oxidizing species. It turns out that the same gas ratio, oxygen to water of 1:3, produces films with an optimal charge storage capacity and also an optimal charge injection capacity. And if you remember from the previous slide, the point that I really wanted to make was, here is the ruthenium oxide, here is the iridium oxide film, could be either, right? And it's ions and electrons that are being transported within the oxide that are important. And this is not really a new idea. Even Domowski from 2002, about 20 years ago, developing supercapacitors, I think, showed quite convincingly that this is electronic conductivity on this line, this is ionic conductivity on this line, and where they're intersecting here is giving you the highest specific capacitance for these ruthenium oxide films, which they controlled by essentially controlling the density of the film. And although I show some gross morphologies of these films, you have to keep in mind that the individual grain-like looking structures in the ruthenium and iridium oxide films are in fact themselves nanocrystalline and have a high degree of water transport and ion transport within those films. And so by appropriately controlling the ratio of electronic to ionic conductivity within the films via controlling the oxygen-water vapor ratio in the plasma, we were able to very convincingly demonstrate to ourselves that this is maximum charge injection capacity. We want this number to be as big as possible, that again, the 1:3 magic ratio produced films that had really actually quite excellent charge injection capacity. In this case, it's 8 millicoulombs per centimeter squared for this particular film. For those of you who are in the business know that that's a very good number indeed. And so there was one problem, however, with the ruthenium oxide, and that was that we find that it is not as robust, and this is a shrinkage of ruthenium oxide under scanning electron microscopy. So we wanted to try to deal with the shrinkage issue. And we did that by making mixed ruthenium titanium oxide coatings. So again, in sputtering system, we have, I think, eight sputtering cathodes. So we can do quite a bit with mixed oxide, mixed compositions. And again, the mixed oxides, this is all ruthenium titanium oxide. And this is increasing sputtering power to the titanium target. And you can see again, change in the morphology of the films. And the thing that we find is that even with any addition of titanium, we get a notable increase in the hardness of the ruthenium oxide, in this case now the ruthenium titanium oxide. So this is hardness, this is versus power, and we see that at the titanium target, this is no titanium, we have a modest hardness. Adding the titanium about doubles the hardness, which is great, but the problem is it also decreases a little bit anyway, the charge injection capacity. So this is on the bottom here. Here is the ruthenium oxide without titanium. We add a little bit of titanium. You see, in this case, almost a factor of 2 decrease in the ability of this coating to deliver charge to tissue. It may actually be that these values are perfectly useful, good for clinical applications. We're not entirely sure. We will have to be investigated in a little bit more detail. But clearly, we are able to control the hardness of the films, and I suspect increase their stability by the addition of titanium. But of course, the one thing that's necessary in all of this is long-term stability. Right? So you're going to put these in the body for decades. And so the way you assess long-term stability is just by delivering a lot of stimulation pulses. And so this data shows the response of a ruthenium oxide electrode. So in this case, 1 billion, actually we're about 1.5 billion now. And I think the point you want to look at really is the bottom 3 graphs from 0 to 1 billion cycles. The properties that we're monitoring, the charge storage capacity, the impedance, these are very constant over these 1 billion cycles. So we're very encouraged that this is going to be a very stable material. So let me finish up quickly here in a couple of slides. And so to summarize, using the water in the plasma, water, and water for sputtered iridium oxide, ruthenium oxide, and mixed ruthenium titanium oxides, we were able to develop coatings that had very high charge injection capacities, comparable to, or at least generally better than what we've seen before from other coatings we've worked with, or from what else has been reported in the literature. So I think that that's very exciting for us, and it really brings us to the conclusions, which is adding water vapor, whether you like it or not, in your sputtering chamber really is very effective at producing films with the right kind of morphology, the right kind of ionic and electronic conductivity within the bulk of the film itself to give us really good charge injection capacity for neurostimulation applications. And we find it's the same for ruthenium oxide as it was for iridium oxide. And while the jury is still out on the ruthenium titanium oxide, we know we have decent charge injection properties, but we do have to think about whether the trade-off of adding titanium is worth it. We don't know yet whether the titanium addition is necessary or not. But that's really sort of an interesting little bit of deposition science that we'd like to study over the next year or two. And then the last thing is, and this is the caveat that you have to put with everything, is that these coatings are no good until we have demonstrated their long-term stability in the body. All right, and so that is the next thing to do, is to evaluate the stability of these coatings in chronic animal studies. So with that, I'd just like to acknowledge the people who really do the work. Here are the graduate students in the lab. Currently, this guy's not a graduate student, but here are the rest of the graduate students in the lab. This gentleman, Bitan, did most of the work that you saw. And I'm just showing a couple of people here. This is Atty, this is Felix. They're smiling and very, very happy because they got their PhDs and they now have nothing more to do with the Cogan lab. And so with that, I will thank you very much.
Stuart, on behalf of the SVC, let me thank you for an absolutely astounding presentation. And honestly, if we addressed every question which came in, we would go another 3 hours. So to our attendees, let me select a few questions and just remind folks that you can send your questions into 2021questions@svc.org, and we'll make sure that they get over to Stuart. So the first question, Stuart, is, have any studies been made to assess whether the water vapor affects surface mobility during deposition and or the energetics of the sputtering environment?
Yeah, no, not really. Right? And what we would expect is that it would probably do both. But we really have not, at least in our lab, delved into the mechanics of the process at that detail and level. But we have to presume that, you know, the amount of water that is condensing, maybe not quite the right word, but the amount of water that is absorbing onto the surface of the films during deposition is quite high.
Next question which came in, which is, there's a theme on a few of the questions, but is, have you tried to use hydrogen peroxide instead of water vapor?
No.
Any differences?
No, that's an interesting point. I had actually not thought of using hydrogen peroxide. That's perhaps blinders on my part. We use hydrogen peroxide to test the stability of electrode coatings because it's so oxidizing. But no, we have not tried to introduce hydrogen peroxide into the plasma.
Guarantee you'll get some suggestions from this great group of stakeholders.
That's a very interesting idea, yeah.
In the SVC. Last question. A couple questions came in about other noble metals, platinum, gold, which appear to have a broad range of oxidation potentials. Can you comment on those other materials?
Yeah. So platinum really doesn't develop a thick enough oxide coating as ruthenium and iridium do. And so platinum tends to be a near monolayer type of coating that undergoes an oxidation reduction reaction involving oxygen. So you're going from platinum to platinum oxide back to platinum. And it is, you know, and we have not been able to build a thick enough coating to do more than obtain just surface reactions with platinum. Gold generally is a bit of a bad actor as a electrode coating. It tends to dissolve. Is presumably the gold is, you know, what species we're forming when we oxidize and reduce the gold are somewhat soluble. Rhodium actually is another possibility, but it's a bit expensive. And of course, one of the motivations, I should say, for us selecting ruthenium is the fact that it's about 1/10 the price of iridium these days. So for a university, that's a big difference. And so, you know, so I think that essentially answers that question, actually, before I go on to go on.
Well, again, let me close the Q&A. Thank you again on behalf of the SVC for an absolutely outstanding